So hi, good morning. TS Muhammad Fauzi, our lecturer for Control System Session 6 for my class. So this video is for our presentation Group 1 for S7 Control System. So next is I will introduce my group member. So before that, I will introduce myself. My name is David Teo Longwei. My metric card is CE19046. So this for next is our group member is Gian Yao Kiat and Vanessa. So next for my part is I will introduce part is first is modeling of electromechanical system. So modeling of electrical system is electrical convert to mechanical component to generate a mechanical output by an electrical input. So amateur control method is used to control direct current DC motor with combining with gear system. So rotational of a mechanical system include the spring, damper, and inertia. So gear is to increase or reduce regular velocity and torque. So gear add in a rotation system as to do lever in resisting system. So if a torque is applied to a mechanical rotation mechanism, is resisted because of the moment of inertia, elastical and mechanism friction by opposite torque. So the torque applied and the torque opposed are in opposite direction, and the algebraic sum of the torque acting on the mechanism is 0. So next slide is the closed loop position control system. So closed loop position control system as a feedback is the concept of an open loop system as it forward part, but it has one or more feedback loop between its output and input. So it does this by generating an error signal, which is the difference between the output and the reference input. So for the next slide, we do the project also. We put the literature review, where is to study in finding the manually and method on setting the PID controller, advantage and disadvantage of the method, and other of the finding that we have done, such as the number 1, number 2, and number 3. So what we find in the Google and research, and the topic is first topic is we find is combination of PI and IP controller by using Ziegler-Nichols turning method for speed control of DC motor, where the find is to find the difference between PI and IP controller in stability analysis, advantage and disadvantage on the both controller. So next we can see is comparison of PID controller turning method, where it focus on analytical classical technique versus optimization algorithm. So the finding is to find the advantage and disadvantage of the turning method on the application. So next, an implementation of PID auto turning procedure in PLC controller. So to finding the sensitivity due to measurement noise that will impact error on the auto turning. So in the report we have put other that literature review that we have finding in the Google about related to our assignment project. So that's all for my presentation video. So thank you.
My name is Vinisa anak perempuan V Parimalam and my metric number is 190098. So today I'll be presenting about methodology. PID controller is a closed loop system which has feedback control system, and it comprises the process variable, feedback variable, which set point and generate an error signal, and according that it adjusts the output of system. This process continues until this error gets to 0 or process variable value becomes equal to set point. Here are several methods of PID controller and getting desired response: trial and error and method. So we have like 4 methods to PID controller. So for A, we use process reaction curve technique. For B, we use Ziegler-Nichols method, C, relay method, and D is using software MATLAB. We choose using software method to solve the mathematical model problem of DC motor in this project. If we see, this is the block diagram and this is the motor DC motor system diagram. So implement of PID, PIPD controller and how it works. So for this construction, we create each PID, PID controller by using step signal PID controller, some integral scope. Some applications use PID controller in cascaded network where 2 or more PIDs are used to achieve control.
Hello, greeting to Dr. Muhammad Fauzi bin Zakaria. I'm Ganakyat. I'm from Group 1. So today I want to present about the result of our group assignment. Okay, so the figure 1 shows the model of the simulating for PID controller with manual tuning, and the figure 2 shows the subsystem in the simulating for PID controller with manual tuning as well. So this is the properties of the PID controller with automatic tuning. So the maximum overshoot percentage is 10.3%, while the rest time is 0.0604 seconds. The setting time is 0.663 seconds. The peak time is 1.10 seconds. The steady state error is 0 due to the gain margin is approaching to infinity. So the figure 3 shows the graph of the step response for PID controller with automatic tuning. And the figure 4 shows the graph of the step response for PID controller with automatic tuning compared with the system response without the controller. Okay, so figure 5 shows the model in the simulating for PID controller with manual tuning, and figure 6 shows the subsystem in the controller with manual tuning. Okay, so this is the properties of the PID controller with manual tuning. So the maximum overshoot percentage is 0.0%. The rest time is 0.0102 seconds. The settling time is 0.0196 seconds. The peak time is 0.99 seconds. While the steady state error is 0 due to the gain margin is approaching to infinity. So the figure 7 shows the graph of the step response for PID controller with manual tuning. While the figure X shows the graph of the step response for PID controller with manual tuning compared with the system response without the controller. So the figure 9 shows the model in the simulating for PI controller, while the figure 10 shows the subsystem in the simulating for PI controller. So actually the model and the subsystem in the simulating is same for every controller. Just the controller is changing. Okay. So the figure 11 shows the graph of the step response for PI controller, and the figure 12 shows the graph of the step response for PI controller compared with step response without the controller. So the figure 13 shows the graph, show the model in the simulating for PD controller, while the figure 14 shows the subsystem in the simulating for PD controller. The figure 15 shows the graph of the step response for PD controller, while the figure 16 shows the graph of the step response for PD controller compared with the step response without the controller. Okay, so the figure 17 shows the model in the simulating for P controller, while the figure 18 shows the subsystem in the simulating for P controller. The figure 19 shows the graph of the step response for P controller, and the figure 20 shows the graph of the step response for P controller compared with the step response without the controller. Okay, so the figure 21 shows the combination of the PID controller with automatic tuning, manual tuning, the PI controller, PD controller, and the P controller. So all of this we will see in the scope and observe their step response. So the figure 22 shows the graph of the step response for PID controller with automatic tuning, PID controller with manual tuning, PD controller, PI controller, P controller, and the step response without the controller. Okay, so for analysis, according to the result of the step response for PID controller with automatic tuning, PID controller with manual tuning, PD controller, PI controller, and the P controller, among all these controllers, the PID controller with manual tuning has the shortest rest time, settling time, and peak time. So the PID controller with manual tuning also has the lowest maximum overshoot, which is 0%. Well, due to the PID controller with manual tuning has infinity gain margin, so it has 0 steady state error. Thus, the performance of the controller can be rated as the PID controller with manual tuning has the highest performance, followed by the PD controller, P controller, PID controller with automatic tuning, and the last is the PI controller. So with the use of the controller into the system able to achieve the desired value, which is the 0.x cm in the minimum time. So the controller also can monitor the system and make sure the system maintain at the desired value. A system with controller is called as a feedback control system, and the controller can change the variable according to the feedback system and form a cross loop. Any changes that the controller makes will affect the desired value and therefore form a cross loop with the feedback system. According to a result, the system step response without the controller unable to achieve 0.x cm in 5 seconds. So the PID controller able to achieve the desired value in the shortest time and has the lowest maximum overshoot. Therefore, the PID controller with manual tuning has the best performance to control the system. Okay, so now I'll show the demonstration for the Simulink. Okay, so before we running the Simulink model, we must first run the M file for the Simulink, which is all the data. So we run first. And this is our Simulink model. First, I will show for the PID controller with automatic tune. So first, we must run the Simulink for 5 seconds. So we run. Okay, so we can observe the step response in the scope. So this is the PID controller with automatic tune. As we can observe, the PID controller able to achieve the 0.8 around 2 seconds. So we can compare with the system set response without the controller. So as we can observe, the system set response without the controller only able to achieve 0.4 in 5 seconds. So with the help of the PID controller, the system able to achieve 0.8 around 2 seconds. Okay, so next. This is the PID controller with manual tuning. So the system able to achieve 0.8 around 1 point something. So it can prove that this PID controller has the shortest setting time, rising time. Okay. Okay, so this is the PD controller. The PD controller will achieve around 1.25 something. 1.25 seconds. So the next is the PI controller. So the PI controller are able to achieve around 4.5 seconds. Well, this is the P controller. The P controller able to achieve around 1.77 seconds to achieve the 0.8. Okay, so last we can see this is the model for PID controller combined with the system set response with the controller, PID controller with manual tuning, PI controller, PD controller, and PLP controller. And all these 6 we can see in the scope. So this is the state response for all these 6. So for this, we are easier to compare the controller. So as we can see, the blue color one is the system, the PID controller with manual tuning. So it has the shortened rest time, setting time to achieve the 0.x second. So the followed by is the green color. The green color is the PD controller. So it can achieve at 1.25 second to achieve 0.8. And followed by the purple color, the P controller. And the next is the yellow color. The yellow color is the PID controller with automatic tuning. So the last is the PI controller. Okay, so that's it for me. Thank you.
So, for the conclusion, the PID controller is the workhorse of modern process control system. The proportional, integral and derivative control modes each fulfill a unique function. Proportional and integral control modes are essential for most control loops, while derivative is useful only in some cases. As a conclusion, the results from both manual calculation and software simulation shown a significant result which proves it is correct and the output is significant to each other. This proving that this assignment is completed with a desired result same as the instruction of the assignment. Thank you.